There is a building technology that predates the Roman Empire, costs a family of $40 a month in energy bills, and has a documented lifespan measured in centuries. Yet across the United States, fewer than 10,000 of these homes exist today. And in most jurisdictions, you cannot even legally build one on your own land. This is called an earth-sheltered home, and this is the extraordinary story of where they came from, the physics that make them work, and the policies and approvals that keep them out of reach for most of us. In the winter of 1804, the Lewis and Clark expedition was camped on the Missouri River in North Dakota, and they were in serious trouble. Temperatures plummeted, and inside the frontier fort, the temperature dropped to 45 below zero. Ink froze solid. Hunting parties returned with frostbitten limbs, and the Missouri River froze hard enough to lead teams of horses across the ice. Yet just a few hundred yards away, the indigenous Mandan people they were camped beside were hosting social gatherings and functioning as if they were oblivious to the fierce winter conditions around them. They weren't burning any more fuel, nor were they any better dressed. The difference here was in their dwellings. You see, in response to harsh winter conditions in a time known as the Little Ice Age in 1400 AD, the Mandan had developed a superior shelter style that proved remarkably resilient to these extreme temperature drops. The floor was leveled at ground level, though often appearing slightly recessed, with a heavy timber frame supporting a thick layer of willow, grass, and packed earth. From the exterior, it looked like a low hill with a smoke hole, but inside was a spacious circular dwelling with a 20 to 65 feet diameter. They called it the Earth Lodge. Soon, the Earth Lodge became the signature architectural form for tribes along the Missouri River. But the benefits of earth sheltering were not exclusive to these plains. In fact, civilizations across nearly every era and continent have turned to the earth for shelter. As far back as the Neolithic era, communities utilized turf and stone to insulate roundhouses, often partially recessed into the ground to break the force of Atlantic winds. While in the arid regions of the Middle East and North Africa, subterranean pit dwellings, dating back over 8,000 years, were designed specifically to mitigate the twin threats of intense solar radiation and abrasive desert winds. But perhaps the most ambitious examples remain the subterranean cities of Cappadocia, Turkey. Parts of these complexes are nearly 3,000 years old, representing a pinnacle of early Earth shelter engineering. Reaching depths of up to 200 feet, these multi-level networks supported thousands of inhabitants and their livestock, carving the soft volcanic tuff into sophisticated urban centers complete with ventilation shafts, fresh water wells, and massive stone doors for defensive perimeters. But to understand what makes earth-sheltered homes perform the way they do, you first need to understand what they are not doing. The insulation in our homes works by slowing heat transfer. It's the barrier between inside and outside, slowing the inevitable alignment of the temperature inside your house with the ambient air outside. And this approach works fine when the temperature difference between the interior and exterior is moderate. But when that differential reaches 50, 60, or 70 degrees, it becomes ineffective at maintaining internal temperature. The cold, or heat, quickly penetrates, and systems burn more fuel to replace the heat that is continuously being lost. Earth-sheltered homes, on the other hand, rely on thermal mass to regulate interior climates. Where insulation resists heat transfer, thermal mass absorbs thermal energy during periods of surplus and releases it during periods of scarcity. And the single largest source of thermal mass available to anyone, at no cost, is the ground itself. At a depth of just 1 foot below the surface, daily temperature fluctuations become negligible. Across most of the continental United States, ground temperature just 3 feet below the surface holds at a near constant 50 to 60 degrees Fahrenheit year-round, regardless of what the weather is doing above. Because that energy is absorbed and released slowly, a thermal lag develops between the exterior conditions and the interior response. The peak heat of the afternoon does not reach the interior until the cool of the evening. The coldest point of the night does not penetrate until the warmth of the following day. In these structures, daily temperature fluctuations are not just moderated, they are effectively flattened. The superior thermal mass of the Earth does the heavy lifting, reducing its inhabitants' reliance on external heating and cooling systems. But even when supplementary heating and cooling sources are required, Earth-sheltered homes ensure a far smaller temperature differential between the inside and outside walls, significantly reducing their energy usage. A building surrounded by earth only needs to close a 15-degree gap to reach a comfortable interior temperature, whereas a conventional home exposed to 20-degree winter air needs to close a gap of 50 degrees or more. In the world of the earth-sheltered homes, 3 distinct building configurations exist, all of which utilize the thermal mass properties of the earth. Similar to the Mandan people, the bermed structure is built at or just below ground level, with earth banked against one or more exterior walls. The remaining facade stays exposed, typically oriented south to capture solar gain through winter. This is the most accessible configuration for builders working within conventional permitting systems and the least vulnerable to subsurface drainage complications because it sits above the water table. The in-hill configuration sets the structure directly into a slope, with earth covering the roof and 3 sides and a single wall left exposed. It maximizes the thermal properties of the ground while still allowing conventional window placement on the exposed face. Earth-sheltered technology in Mankato, Minnesota, which has built over 650 homes to this design since 1981, records interior temperatures that never drop below 50 to 55 degrees Fahrenheit in midwinter with no supplemental heat. The fully underground configuration recesses the entire structure below grade. A central atrium or courtyard is usually excavated to bring light and air into the interior. These require the most rigorous structural engineering, as the roof must carry the full weight of the overhead soil, and drainage must be designed with the same precision as the thermal system. But they offer the highest degree of weather protection and the most stable interior temperatures of the 3 types. The theoretical case for earth-sheltered construction has been established for decades, but what the last 50 years have produced is a commercial track record substantial enough to put hard numbers on it. For starters, their energy efficiency compared to traditional homes is significant. Oak Ridge National Laboratory conducted continuous hourly thermal measurements on a 4,000-square-foot earth-covered building beginning in 1982. They found 30% heating savings and 26% cooling savings compared to an already energy-efficient above-grade structure. Peak cooling requirements were 50% lower, meaning the mechanical systems required were smaller and cheaper to run. Perhaps most importantly, 90% of the occupants reported being comfortable at all times. The upper bound of efficiency, documented by earth-sheltered technology across its portfolio, reaches 80% savings over a conventionally built home of equivalent size. In one case, a 6,000-square-foot home for a family of 5 incurred just $40 a month in total heating-related utility bills. A 1980 HUD commissioned study by the University of Minnesota found that earth-sheltered homes also carried resale values 30 to 40% higher than equivalent wood frame construction. And, as they are essentially underground bunkers, their tolerance to natural disasters is also extremely high. Earth-sheltered homes generally offer superior earthquake resistance compared to conventional above-ground structures because they move with the ground rather than shaking independently. They're also sheltered from the 200-plus miles per hour winds of tornadoes, and as these structures often have no exposed timber framing, asphalt shingles, or wooden roof deck, there is no meaningful fuel load for a wildfire. As a result of this, insurance underwriters who have assessed earth-sheltered homes have rated them at dramatically lower risk profiles than conventional construction, with premiums in some documented cases running 50 to 90% below a standard policy for comparable square footage. All right, so it's clear that earth-sheltered homes are both more energy efficient and more durable than traditional builds, which open the question as to why there are fewer than 10,000 of these homes in the United States. And the answer likely comes down to a multitude of answers. The most obvious barrier is building codes. The International Residential Code, which governs most detached residential construction across the United States, contains several provisions that can make designing earth-sheltered homes challenging. For example, every habitable room must have at least one operable emergency escape opening and a glazing area equal to 8% of its floor area. Another regulatory issue many homeowners run into is the bureaucratic system's unfamiliarity with these plans. Earth-covered roofs, which can carry 10 to 20 times the load of a standard roof, require specialized structural engineering calculations that many municipal building departments have never reviewed and are not equipped to assess efficiently. Permits that take weeks for a conventional home can take months or years for an earth-sheltered one, adding tens of thousands of dollars in review fees before a yard of concrete has been poured. But there are also genuine practical limitations that any honest account of earth homes must include. Construction costs run 10 to 20% higher than equivalent conventional builds at the outset. The long-term savings in energy and maintenance are well documented, but that initial premium is a real barrier for buyers who cannot access conventional mortgage financing, which itself is complex due to the unique nature of these properties. Moisture management is also an extremely important technical challenge that requires serious consideration. Williamson Hall at the University of Minnesota, a landmark earth-sheltered building completed in 1977, is now scheduled for demolition due to chronic mold and water infiltration. Building below the water table will inherently cause problems that must be seriously considered during the planning phase. There is also a psychological dimension of living in a home like this. Studies of occupants in underground and earth-sheltered environments are more likely to feel a sense of isolation, reduced control over natural light, as well as anxiety about egress in an emergency. Of course, a well-designed home can eliminate this with south-facing glazed walls, light wells, and biophilic interiors. But again, these are all things that should be considered during the planning phase. But for those determined to build an earth-sheltered home, several paths exist. The right one depends on budget, location, and how much of the work you are willing to do yourself. The first step for any builder is understanding the jurisdiction limitations. 16 states leave building code adoption to individual counties rather than imposing a statewide standard. Within those states, certain counties impose minimal or no residential building codes at all. In Colorado, Delta County and Saguache County, for example, require no building permits for unincorporated land and host the highest concentration of alternative builders in the country. For those building in jurisdictions with active codes, some pathways exist there too. The 2021 International Residential Code includes Appendix U, covering cob construction, the first time an earthen building method appeared in an international code. As for the structure itself, 4 approaches exist at different price points. The most accessible entry point for owner-builders is the post, shoring, and polyethylene method developed by Mike Oehler, who built his first underground home in northern Idaho in 1971 for $50 using salvaged lumber. The method uses structural timber posts set into the ground, horizontal shoring members forming walls and roof, and a layer of polyethylene sheeting protecting the timber from soil moisture. Oehler's book on the method went through 7 editions and 14 printings, and remains the lowest cost entry into earth-sheltered construction. Earthbag construction, also called super adobe, uses polypropylene bags filled with subsoil, stacked like masonry, and tamped flat between courses with barbed wire providing tensile strength. Shell costs run between $33 and $35 per square foot. CalEarth, in Hesperia, California, founded by architect Nader Khalili, teaches this method and offers workshops ranging from a 1-day basic session to a 10-week apprenticeship. Their structures have passed California earthquake code tests and won the 2004 Aga Khan Award for Architecture. But for those wanting a fully engineered, mortgage-eligible result, established commercial operators have refined the process into a repeatable product. Earth-sheltered technology in Mankato, Minnesota, builds all concrete reinforced steel shells at approximately $150 per square foot before interior finishing, with completed homes running between $340,000 and $840,000, depending on size. Formworks Building in Durango, Colorado, uses a patented bolt-together steel framing system covered in rebar and shotcrete, meets all current building codes, and carries Fannie Mae and Freddie Mac mortgage approval. And Davis Caves in Atlanta, Illinois, offers an octagonal poured concrete design and has completed more than 300 homes across the country. Whichever path is chosen, 2 elements must be treated as non-negotiable regardless of budget. The first is drainage. A subsurface drainage system with foundation drains set in a gravel bed must be in place before backfilling begins. Naturally permeable soils such as sand and gravel are ideal for backfill, as they allow rapid percolation away from the structure. The second is waterproofing. Standard damp proofing is insufficient. High-performance membranes, rubberized asphalt, bentonite panels, or liquid polyurethane, applied to all earth contact surfaces, are the minimum standard. The waterproofing system is what determines whether a structure like this is still performing in 50 years. For anyone wanting to learn the process hands-on, the core reference library for any serious builder starts with Mike Oler's The $50 and Up Underground House Book, Rob Roy's Earth-Sheltered Houses, and Malcolm Wells' The Earth-Sheltered House. These three texts cover every major construction method, permitting strategy, and design principle the research has validated. The Earth-Sheltered Home is a building method refined over centuries with a proven energy efficiency and structural durability that conventional construction simply can't match. If you enjoyed this story and want to learn about a structure the American Institute of Architects deemed to be the strongest, most lightweight structure known to man, then make sure to check out our video on geodesic domes next.